Our formula is the following. We give 35 minutes, but this includes questions.
Okay, so 30 minutes. So let me know when I can start.
So we start this session, and the first speaker is Professor Victor Nistor from University of Lorraine, and he will speak about lower potentials on manifolds with cylindrical ends and the Laplace operator. So please start.
Thank you very much. I hope that none of you is personally affected by the terrible current events. So I will talk about layer potentials, and I see that there are many people that work on hardcore partial differential equations, so that fits into that framework. But also I will use quite a few ideas from what some people call index theory, so hopefully that should please more people. So this is joint work with several co-authors. So here's the plan of my talk. First, I will review the layer potentials, the method of layer potentials on an open subset of Rn. Then I will quickly discuss Fredholm operators, the index and invertibility, and how this relates to invertibility. And then I will apply these results to manifolds with cylindrical ends. Now, the index theory that I will use not fancy at all, but it has some trivial consequences. So more precisely, the index theory appears in the following way. It appears through the following rather trivial, I would say, result, which says that if T is Fredholm, so remember Fredholm, of index 0 and injective, then T is actually invertible. So of course, this is a triviality, but it's interesting that actually index theory can be used to prove that a certain operator is invertible, and I'm happy to see here so many people among the speakers who are interested in index theory, and of course the list is far from being complete. Okay, so the goal in the method of layer potentials, our goal in general in this talk, is to solve the Dirichlet boundary value problem. Laplacian of u is 0 inside the domain, and u is equal to f on the boundary, a very classical problem. And well, for some reasons, we want to use the method of layer potentials. There are several reasons. It's a very classical method, maybe one of the first ones used for this problem. It's a method that is useful for numerical methods. It yields also results on the Dirichlet to Neumann map, and we can think of many other reasons. So what is this method of layer potentials? So let's forget for a second the boundary and recall that the solution of just Laplace of v is equal to h, a compactly supported continuous function on Rn, is given by an explicit formula that I'm sure everybody knows, which is v of x, the inverse of the Laplacian applied to h, is given by some constant that I will usually forget to mention, times this integral. So this integral is the convolution of h with the fundamental solution of the Laplacian. So it has an explicit formula. The method of single layer potentials then is to look for the solution to our boundary value problem. So a solution to our Dirichlet boundary value problem that is of the following form. U of x is the inverse Laplacian applied to some distribution supported on the boundary. So more precisely, g times the conditional measure on the boundary. Of course, this is given by the explicit formula above. The integral this time on the boundary of the convolution with the fundamental solution times g of y times the measure, the surface measure. And this operator, we call it S of g, is the single layer potential applied to g. And here g delta of the boundary is, of course, a distribution that is supported on the boundary. And this is important for us. Okay, so here I repeat the definition of the single layer potential. Single layer potential of G is the inverse Laplacian applied to G times the delta on the boundary, given by the explicit formula. Sigma is the surface measure on the boundary. And this distribution applied to a function h is simply the integral of h times the density G on the boundary. Okay, so this is a distribution that is supported on the boundary. In particular, it's 0 in the interior. So the single layer potential applied to G will turn out to be a harmonic function in omega. So what does this give us? It gives us a very large supply of harmonic functions in omega. But in order to solve our boundary value problem, we need to find a function G such that S of G, the single layer potential applied to G, matches the boundary, the desired boundary conditions. Okay, so this may or may not be trivial, but it reduces solving the Dirichlet problem to inverting the operator S. Now, in fact, well, at least for this talk, it's easier to work with a slightly different operator, which is the double layer potential operator, which looks very much like the single layer potential. So its inverse Laplacian applies to H times, this time not the delta of the boundary, but the normal derivative of this distribution. So this also has an explicit formula. So the difference between the formula for the double layer potential that is here and the previous formula is in magenta, this type of funny red, which is that we put a prime here and we took this normal derivative here. Otherwise, it looks exactly like the single layer potential. There's, however, a very important difference, which is what happens when we look at the boundary value problem, boundary values. So to get the boundary values, we will take the non-tangential limit as x goes to z on the boundary. And what do we get? Well, we can try to formally pass to the limit here. And if we formally pass to the limit, we obtain this term, which you see looks exactly as the one above, except that here z is on the boundary, whereas before x was in the interior. If x is in the interior here, there's no problem integrating that. When z is on the boundary, actually here we have a critical singularity, and this integral is defined in terms of principal value. And because of that, actually there is this additional term, this h of z divided by 2. And we write the result as k plus 1/2 of h, k being this operator with principal value. Okay, so as before, to solve this is going to be harmonic in the interior. So to solve the Dirichlet boundary value problem, it is enough to match the boundary conditions. That is 1/2 plus k applied to h is equal to f. And we will study this equation using this index theory that I mentioned above. So we want to show that this operator is invertible using that pattern, okay, that paradigm. Okay, so this repeats what I have just said. Our Dirichlet boundary value problem, Laplacian of u is equal to 0 and u is equal to f on the boundary, is equivalent to solving this operator equation, 1/2 plus k applied to h is equal to f. Okay, also recall that up to a factor, which I said I'll usually forget, k is the integral operator with the kernel described here, normal derivative of the Newtonian convolution kernel. And if we do the calculation, we get this term. And if the surface is smooth, this z minus y as z goes to y will tend to be normal to the boundary. So this will give us an additional vanishing. And what this means is that if the boundary is smooth, then k is an order -1 pseudodifferential operator. So without that additional vanishing, we would not get that. So that in particular means that if the boundary is not smooth, this method will not work as easily as in the smooth case. Okay, and then we'll use the fact that an order -1 pseudo-differential operator, in our case this capital K, on a compact smooth manifold is a compact operator. In fact, I think it's kind of this type of problems that have led people to study compact operators, and then it has blown up into operator theory and other subjects. So this happened at the end of the 19th century. But the method of layer potentials is even older. It goes back to Gauss, you know, when he lived. Okay, moreover, if in addition to being smooth, if the domain is, if the boundary is also bounded, then K will be an order -1 operator on a compact manifold, so it will be compact. Okay, so now let me show you how we solve with this method the Dirichlet boundary value problem in the smooth compact case. So it works as follows. Since K is of order -1, we know that it is compact. We have just discussed this. And hence, the operator 1/2 plus K, which I'll call P for ease. So 1/2 plus K will be Fredholm of index 0. This is index theory 101. Okay, so the index means the dimension of the kernel minus the dimension of the kernel of T star. So that I said is 0. The next step is to show using energy estimates, this still comes in. So using energy estimates, we show that there is the operator P1/2 plus K, which we study, has 0 kernel. So it's injective. Well, and then bingo. So we have an operator of index 0, Fredholm operator of index 0, that is injective. So it's invertible. And then our solution, as I have explained before, the solution of our Dirichlet boundary value problem, U, is the double layer potential applied to P-1 of F. Okay, and that will match the boundary conditions. Okay, and we want to extend this method to non-compact manifolds, in this case to manifolds with cylindrical ends. Okay, so let's assume this time that omega is a domain in a smooth manifold. So we replace Rn with M. The first issue is that the Laplacian will generally have a kernel. If the manifold is compact, it will have kernel, the constant function. So how can we proceed then? Well, we'll use a trick. Okay, so we'll have to do some modifications, which I'll call the Mitra-Taylor trick. And it works as follows. We replace the Laplacian with the Laplacian plus V, where V is a function that is greater or equal 0, but not identical equal to 0. And I didn't say that. It should vanish on omega. Well, so it should vanish on omega, so our operator will still be the Laplacian inside omega. Okay, and then delta plus V will become invertible if V is non-identically 0. And then we define the single and double layer potentials, S of F and D of F, using similar integrals, similar formulas, but replacing delta -1 with delta plus V -1. Okay, and the jump formula remained the same. And then what do we do with this operator? In fact, okay, I have not justified, I will do that now. Why is delta plus V invertible? So let me do that. So V is in C infinity, V is 0 on greater or equal to 0 on M. It is 0 on omega. We require V not to be identical equal to 0 on M. If we have something non-compact, it has to be non-zero also at infinity, whatever this means. And okay, now let's go to the case smooth and compact. So first of all, delta plus V is positive as an operator. So it's self-adjoint because it's self-adjoint and because it's formally self-adjoint and elliptic. Let's show that it's injective. We prove injectivity using energy estimates as usual. So we write 0 is delta plus VU in a product with U. We separate, and we get from this, both terms are supposed to be positive. We get du is 0. That means that U is constant or locally constant. Since VU is 0 and V is not identically equal to 0, we obtain that U is actually 0. So that constant must be 0. So that shows that delta plus V is injective. And then bingo again, with that simple Fredholm theory or index theory result, we obtain that delta plus V is invertible. Okay, and this carries through to manifolds with cylindrical lengths or domains with cylindrical lengths, but certain things will not be quite as direct as explained here. And the things that are more difficult or are different are in red. So first of all, we require V to be non-zero also at infinity. That is to be expected. Proving that it's Fredholm of index 0 will not work by the same argument. Well, actually, it may work in this case, but maybe not for other operators. And then, at least for the Stokes operator, this L2 unique continuation property is not so trivial. Okay, so let's now move to manifolds with cylindrical ends. What's a manifold with cylindrical ends? We start with a compact manifold with boundary M bar, which is depicted here to the left. Okay, so it has this boundary and this tubular neighborhood. And what we will do is that we will attach to the boundary a cylinder, a half-infinite cylinder, whose base is the boundary. Okay, and that will give us our manifold M. So M is the compact part with boundary, which is M bar. And then the half-infinite cylinder has as base the boundary of M bar, and it's half infinite, so it's times minus infinity 0. I like to start from minus infinity because that fits better with the Kondratiev transform. In fact, we want to use our results for domains with cylindrical lengths. This is very similar, and I won't write a formal definition, but we have here some pictures. These domains with cylindrical lengths may happen to be, actually, we will consider them to be contained in some manifolds with cylindrical lengths and without boundary. So here the big thing is the manifold without boundary, and the bigger thing that sits inside is the manifold with boundary. They both have cylindrical lengths, and you see that the ends match in a certain way. Okay, so why are we looking at manifolds with cylindrical lengths? Well, this is because that's a way to approach manifolds with conical points, and they have been used a lot in the literature studied a lot in the literature because they are the simplest domains with singularities. There are many people who studied them. Here I put mostly the people who used approaches close to ours. So even in this case, the list is pretty long. While Kondratiev, for instance, didn't use layer potentials, so that's why I didn't include him in this list. But of course, he has some great results, and we'll see some of them. Okay, so we want to study these manifolds with cylindrical lengths, and we'll look at the Laplacian. We'll take a metric that is straight on the cylindrical length, and then the Laplacian will have the following form. I take the positive Laplacian. So t is the variable on the cylinder, so it's minus dt squared, and then plus the Laplacian on the boundary, just on the boundary. And if you think a little bit about it, so we have this half-infinite cylinder, but if we are far away towards minus infinity, we can move left and right and do small translations back and forth. And then this operator is invariant under these local translations close to infinity. So this is the kind of operators that we will consider, or very closely related. Okay, and we need to go through the same game as we did on manifolds with boundary. That is, construct a single and double layer potential, construct their limits at the boundary S and K, straight S and Ks, and we need to invert the Laplacian, or more precisely in this case, delta plus V, because the Laplacian will not be invertible as before. Okay, so here are some results. Let's assume that V is greater or equal 0 and translation invariant at infinity. So V will not depend on t close to infinity, and omega is a domain with cylindrical ends. Then Laplacian plus V is invertible on L2 from its domain to L2. Its domain can be shown to be H2. Also, the double layer potential operator associated plus delta plus V is such that 1/2 plus K is also invertible, and hence the Dirichlet problem is well posed. Well, this result was known, but we obtained it through layer potentials, and this has some advantages. Just a word of caution, the K in the compact case was compact. K in our case will no longer be compact. So a different type of approach will be needed. Well, in fact, an improved and enhanced approach. So we don't really change the approach, we just add something to this approach. Okay, and we will consider suitable classes of pseudo-differential operators. In fact, this K, the S, they're all pseudo-differential operators. So that's why we like them and we study them. So what kind of pseudo-differential operators we will use? Well, as like our differential operators, we will use pseudo-differential operators that is locally translation invariant near infinity. So we have this translation. X is the variable on the boundary. T is the variable on minus infinity 0. And we have this translation. And we take operators whose pseudo-differential operators whose distribution kernel is supported in an epsilon neighborhood of the diagonal. So Schwarz kernel supported in this neighborhood distance of xy is less than epsilon. Okay, and also we assume that they are translation invariant in the following sense. If the support of f is very far away towards minus infinity, so it's contained in a set like that, and S is positive, so S pushes us towards minus infinity even farther, then applying P and then translating towards infinity is the same as translating towards, minus infinity is the same thing as translating towards minus infinity and then applying P. So we have this commutation, but it's only for functions that have support far away, that is close to minus infinity. Okay, and then we introduce the algebra of pseudo-differential calculus of pseudo-differential operators with this property. In terms of distribution kernels, this invariance at minus infinity means that if we write the distribution kernel of our operator on the half-infinite cylinder, then it will satisfy this property as long as we are far towards minus infinity, meaning t and minus t prime are large enough. Okay, then psi minus infinity is the intersection of all psi's. Psi infinity is the union of all psi's. We can introduce vector bundles. Okay, these are the usual notation for pseudo-differential operators. And there's one important additional piece of information that many people in the audience, of course, know, which is typical to this situation of either conical singularity or cylindrical ends. This is the indicial operator. So what is the indicial operator? So the indicial operator is the following. Okay, so let's assume that we have one of these operators that is translation invariant at minus infinity. Its initial operator is the unique pseudodifferential operator on the doubly infinite cylinder. So here it's the boundary times R. So it's a pseudodifferential operator on this doubly infinite cylinder, which is fully translation invariant, and it's defined by this formula. So we take an F on this on this fully infinite cylinder. We push this F towards minus infinity. Once we are far enough towards minus infinity, we can let P act. So we let P act, and then we pull it back where we were. We apply phi to minus S. So that's how P tilde is defined. And in terms of kernels, is given by this formula. P tilde of Tx T prime X prime is just P of Tx T prime and X prime. But from T and T prime, we subtract some very large S. Okay, it's the same as a limit is you want, if you want. Can you hear me now? Can you hear me?
Yes, we hear you well.
Okay, because I put my headset.
Okay.
Okay, then P tilde is defined, and it's translation invariant. It has a translation invariance, means that we can add S to both T and T prime for the distribution kernel. Now, of course, these are pseudo-differential operators. If they are of low order, as it is the case for our layer potential operators, then they're actually given by functions. If not, look at this relation for outside the diagonal. Okay, and then in fact we need to extend this algebra of translation invariant at infinity operator by throwing in a few regularizing operator, which will make it almost translation invariant at infinity. But it has the advantage that this time it's stable under inversion. So if we have an operator that is translation invariant at infinity and is invertible in L2, its inverse, however, will not be translation invariant at infinity, but will be almost translation or essentially translation invariant at infinity. So that's why we have to include this modification. In fact, so I'm attributing this to Kondratiev and Melrose and Mendoza because it's very close, but this algebra of essentially translation invariant operators is not contained in the B calculus. It's rather contained in the C calculus. Well, it's not very important. Okay, so here's an important result for us. So let's assume that M is a manifold with cylindrical ends, and P is a pseudo-differential operator that is translation invariant. We have that P is Fredholm if and only if it is elliptic, as is the case on compact manifolds. But we have to add the condition that the initial operator defined before acting on these spaces is invertible. Okay, so this fits into the realm of spectral theory results on the essential spectrum. Again, there's a very long list of people that worked on this. Don't have time to read it. Okay, then our result will work in a similar way. We prove the Fredholm property based on this result. We use the jump relations, and we again arrive at the fact that delta plus V minus 1 and K. First, we arrive at the fact that delta plus V minus 1 and K are essentially translation invariant by the spectral invariance. Then the inverse 1/2 plus K is spectral invariant. Okay, for the Stokes operator, the situation is a little bit more complicated because this behaves more like the Neumann problem, or at least in part. So one has to modify a little bit the operator. We have some results with Mirella and Wolfgang on this. Okay, so here's the conclusion. Although the double layer potential operator K is no longer compact on a manifold with cylindrical ends, we still can carry through the method and we still obtain that 1/2 plus k is Fredholm of index 0, injective, and hence invertible, and that then gives us the well-posedness of the Dirichlet problem. A nice thing about about the approach using layer potentials is that it gives the structure of K and of the inverse, so it gives more precise formula. Thank you very much for your attention. Спасибо за внимание.
Thank you very much for your talk. Questions?
I'll stop sharing.
Yes.
Or not? No.
Vladimir has a question. Please. We don't hear you.
Where is published these results?
The one with Mitra is published in the Czech Journal of Mathematics, Czechoslovak Journal of Mathematics. It's pretty old.
Okay. This is a smooth area, only smooth area, or there are the Mitra results about the bed domains.
Well, we allow
bed boundary.
It's a combination, because we allow in the paper with Mitra, we allow the boundary to be just Lipschitz.
Okay. Okay. Thank you very much.
More questions? Elmer Schroer has a question, please.
Yeah, maybe I missed it. What is the result on the structure of this K and 1/2?
The fact that they are pseudo-differential operators in that essentially translation invariant.
Okay.
So pseudo-differential operator in that al calculus, essentially translation invariant.
That you knew before, right? That they're pseudo-differential, or?
Well, I don't know if in this setting.
Okay.
Well, in general, yes. I mean, on compact smooth manifold, that's a very classical thing. Yes.
Oh, nice.
More questions? Maybe this is not the case. So let's thank Victor Nistor for his talk.
Thank you.
We have a maximum number of online participants during this conference, so we got number 18 at the moment.
Okay, so I will stop sharing, and so Anton, do you want me to do something next? Or maybe I have already stopped sharing.
You stopped. We only see videos of some of the participants who turned on their cameras.
Okay.
So the next talk is at in 5 minutes, and I hope you continue as a chairman of this session. Okay.
Sure.